right?
Okay, good. Yep, I just hit record.
Okay. Okay, so far, is there any question? Let's
Nope.
start from there.
So far, so good. I think we were creating an array, a class,
Yesterday.
my array. Yeah.
Okay. Okay. All right.
So far, so good.
Okay. So far, is the meeting, has it been productive or should it be improved upon?
They've been really good. They've been really productive. I'm learning a lot.
You're not in.
Oh, yes.
Okay. Okay. That's great. If it has been. All right.
Mhm.
Okay. So yesterday we were actually looking at arrays, how to create one, right?
Yes, we did the push method so far.
Yeah. Okay. Basically, that's what data structures has to do with. At least one should be able to know how to create some data structures, because aside the inbuilt data structures, so to say, like objects, arrays, the way they're being used in programming language, when it comes to data structures and algorithm, a programmer should be able to create something of that nature so as to suit whatsoever application he may be building. And also, building a data structure from scratch will help you structure the kind of operations that could be done in an application. Okay, let's shift our focus back to Twitter and Facebook once again.
Okay.
You notice that the features that you have in Facebook, they are quite different, or the operations that can be done on Facebook are quite different from those ones that could be done in Twitter, right?
Right.
Good. Facebook has to do with friendship, while Twitter has to do with followership. Sometimes account A could follow account B on Twitter, and account B will not be following account A. But in Facebook, when a friend request has been sent, okay, and the other account accepts it, both accounts, they become friends to one another, right?
Right.
This person can rightly view the friends of the other account, but there's a kind of restriction on Twitter about that. Okay, that's the essence of what the purpose of being able to build a data structure. Like what I was trying to say yesterday about the codes, when you actually check, there had been a whole lot of codes that implement these data structures. So all one needs to do, just as what you and I know, one can get to Stack Overflow, copy some codes, use it the way he wants, whether he edits it or whether he refactors it. Let me not use the word edit. Whether he refactors the code,
Right.
or he uses it exactly the way it was copied. But the aim of it is to be able to do some kind of things in his or her application. So that's just exactly the way it's all about. Then we are actually looking at, you've been able to understand, okay, of course, you know the push method in array. It adds an element or an item to after the last item in an array, right?
Right.
Good. Then we also have a pop method. Okay, let me share my screen. Oh, sorry.
Okay.
Sorry. 1 second. Oh. I can't share my screen. Can you enable me?
Oh yeah. All right, there you go.
Okay. This was actually where we were yesterday. Okay. Now I'm trying to add a pop method. When you talk about pop method has to actually do with deleting. That's the purpose. But in order for you to delete an item, that means the programmer, first of all, will have to grab that item that needs to be deleted, right?
Right.
Okay. Let's create an item. Let's create a variable of an item. Okay, let's name this item. Let's say that is the last item because that's usually what you need to grab. All right.
Right.
Okay, you remember this data, right?
Yep.
So in order to grab the last item is going to be this data. Okay.
Mm-hmm.
Length -1. Right?
Yep.
Okay. So once you have grabbed it, you can now use the delete keyword to delete the last item in the array.
Mm-hmm.
Okay. And once you've deleted it, you will notice that since an item has been removed, the length of the array will surely decrease. Is that not true?
Yes.
Good.
Mm-hmm.
So you now decrease the length of the array, and let's return something. Let's return the last item. Okay. All right. Let's check whether it will actually work.
Okay.
Delete last item. Okay, sorry.
Oh, this data.
Hello.
Yep.
Okay. We have to grab it in here.
Okay.
Yeah. Okay. We put in yesterday, we were able to push in 3 and 45 and Harry, right?
Right.
Okay, good. So if you check the output here, in my array, we were able to output all these 3 items, right?
Right.
Let's actually call the pop method.
Okay.
And see, okay, let me move it down. Wow. Comes last item. This data.
Oh, length.
This length. Okay.
Oh, yeah.
Sorry.
This.
Remember, we used this length here. I used only length.
Gotcha.
Sorry about
Worry.
the. Okay. So we were able to delete one item here. Okay.
Yeah.
Good. So, and the length of it was able to decrease
Right.
from 3 down to 2.
Yep.
Hello?
Yep, that's correct.
Okay. Okay. So the next other method that we can actually look at is, remember we talked about inserting an item at any index position of the array, like when we use the splice method. Okay, we can now say insert item at, we now take the item that we need to insert and the index where we should insert it.
Right.
Now, for we to be able to do that, that means we have to go through the array from the first index, that's index 0, to the last index. That means we have to loop through it. Then we now use a for loop.
Right.
Okay. Okay. Now we now say that if this is equal to this dot length, okay, if I is equal to this dot length and I is greater than this, and I is greater than the index, okay?
Okay.
The index where we want to insert the item, we can now decrement, okay? And it's now going to give us, we are now going to grab this dot data, okay? Square bracket of I, and we now make it to be equal to this dot data square bracket accessing this minus 1. Okay, remember in an array, the index is, because it starts at 0. So if I want to grab item at position number 3, it's going to be found at the index of 2, right?
Right.
So that's why we are doing the I minus 1.
Okay.
All right. So we can now say this dot data at index will now be equal to the item. All right.
Okay.
And we can now see this dot length, because we've just added an item in the array. That means the length is going to increase, and we can now return this dot data. Oh my God. Okay. Let's see that let's check if it will work. Our new array insert at, let's say, insert, let's say 100 at position number 1.
Okay.
Then let's output array to check whether it's going to work. Okay. You can now see the output.
Yep.
And you can now see that 100 has been inserted.
Yep. But 45 looks like it's missing.
Yeah, 45 is missing. Just noticed.
I have a question for you.
Okay, go ahead.
So for instance, where we say for, and then we said let I equal this dot length, because we could say this dot data dot length, right?
Now, this dot data dot length, from this already, okay, this dot data, we are referring to the arrays itself. This dot length is the maximum number of lengths okay, in the array that you have already established.
Gotcha.
All right. So whether you say this dot data like up here, or you say this dot length, they still make reference to whatsoever the length of the array at this point. So like, for example, if I remove this dot data, it still gives the same answer, right? If I still add this dot data, it still gives the same answer.
Okay. Yeah. So basically, so if you use this dot data dot length, that's kind of like, it's kind of messing up because you're using the data or using the array versus making an array.
Sorry, I didn't get you.
I was wondering, so if you use, like, let's just say if you use the length of this dot data instead of this dot length, that would basically be wrong because you're using the array versus creating an array. Hopefully that makes sense.
If I get you your question right, it's not wrong. Remember, in the constructor of the class, we had already defined the array, right?
Right.
Good. Then we've declared the array and we've declared the length. For each of these methods, like in push, if you push in a data onto this array, we increment the length. It gives the exact number of lengths here.
Right.
Okay. Okay. Now, this is an array that we are building. We are building it. And because we are building it, it's not like the normal array that that is just being declared like the normal way arrays are being declared in JavaScript. It's because we are building it from scratch. Now, for the pop method, once we delete an item, we decrease the length so that the length will correspond to the length of the data.
Gotcha.
That's why at this position, if I run it again, this dot data dot length, it still gives the same answer as removing this dot data dot length.
Gotcha.
You understand? Now we are just building it. We are not trying to rely on, I could have said at this point, like it's going to be this dot data dot pop method.
Right.
Which would have been straightforward and so simple.
Yeah, that would be more simple, but you would be using it built in instead of creating it yourself.
This should have been like just using the built-in method.
Right.
Instead of going through the stress of creating it.
Right, gotcha.
Okay.
So we're not showing, if we did that, we wouldn't be showing our skills, basically.
Hello?
Yep.
Okay, you said what?
I was saying, because if we did that, we'd get it wrong because we weren't using our skills. We're only using the built-in method.
Yes, because that's just the basic purpose of actually doing the code implementation
Gotcha.
of array instead of using the JavaScript built-in method.
Okay, understand now.
Okay. Okay, let's try and fix this this item that's missing. Okay. All right. Okay. Okay, see what I first of all want to do. Okay.
Okay.
I want to assign a variable. Let me say, okay, I've already declared. Okay, let me use that thing. Let it be equal to this dot data. All right.
Okay.
I. Excuse me.
No worries.
Then I actually want to grab, once I've grabbed this item, okay, to reassign it, while this other 45 that has been in here, all right, will be reassigned to the index +1. Okay, I think it's going to solve this issue of 100, the newly inserted item replacing the old one at that particular index.
Okay.
All right. Yeah. Okay, I'm coming. Okay. Let me use an if statement here.
Okay.
Let me comment this one out first.
Okay.
If this is equal to this, okay. Let this dot data I -1 be equal to
Data.
Sunny. Hello.
Yep, I'm here.
Yeah, I'm stuck, but I'm trying to think through. Okay.
No worries. This is good for me. So we're saying if this dot data at the index, so while you're going through, if it equals this dot data I -1. Should we be checking for index there? Where we say if this dot data I is equal to, because we pass index maybe. Oh no, because
No, I'm coming. Okay, if we say this dot data dot index, right?
Mhm.
is equal to this dot data I minus 1. Still gives the same thing.
If this data. Well, because we're passing an index, right? That we want to replace the item at. So maybe if this data at index equal. So I think we should say, yeah, if basically what is currently at the index, we probably should move it to the right and then insert what our item at the index. Data. Okay. Is equal to this data index.
Okay, I think.
Because basically, okay, so when we scroll through, we say if well, I is going to be the index. I is greater than index.
Okay, Sonny. Sonny.
Yep.
Can I suggest something?
Sure.
Seriously, I'm stuck here. All right, and I can't think straight.
No worries.
Let's leave this particular portion. By tomorrow, we handle it.
Okay, that'll be homework.
I promise I'll fix it.
Okay, sounds good.
I promise I'll fix it.
Okay.
I'm sorry about that. I'm not just thinking straight. No.
No worries. I'm sure I'm confusing you with what I'm saying.
No. You're not confusing me. Okay. It happens. Yeah. Sorry about that. Such of my limitation.
No
I'll
worries.
sleep over it and I'll think through it.
Okay. Sounds good.
Okay, yeah.
Okay.
Let me comment out this insert method down here.
Okay.
All right. So then the other thing that could happen in an array is actually assessing using the index of the array, excuse me, to actually get the value of the item at that position, right? So let's say that we want to get an item at a particular position. All we just need to do is just to grab that item. Okay. In order for us to grab that item, we can just say return that particular value at that particular index. Like we can now say return, let's say this does data at a position. We'll pass in index here, right?
Yeah.
So we can be able to say index minus 1.
Right.
Okay. New array dot get item. Let's say at index of 1. Let's see if it is going to work. Sorry, we'll just have to output this. We just have to output this because what is it called? It's not going to add to the array.
Oh yeah.
Yeah. So we got 3. Okay. 3 is the first item. That's at index 0. This minus this. Oh, sorry, index minus 1. That's 1 minus 1.
Right.
That's 0. Then if we see at 2, okay, we'll be able to get 45. All right.
Gotcha.
Okay. So these are the basic operations in an array.
Okay.
These ones we will fix them by tomorrow. Please pardon me for that.
Yep, sounds good. No problem.
Okay, thank you. So that this basically how one can implement his own array data structure by building one for his own purpose. Yeah. Okay. See what I intend to do for you. I intend after everything, all these codes, okay, I will actually write them very well with comments and send them to you.
Okay.
Will that be good?
Oh yeah, that'd be perfect.
Okay.
So when we do this, this is basically because yesterday we wrote access, search, insertion, and delete. Are those the same? Are you do that for every data structure that you create?
Okay. I wouldn't say it works out for every data structure. Okay. Let's quickly go back to the Big O website. That's Big O cheat sheet website. Okay. Yeah. Because when you actually look at one of the operations for hash table, okay, you find out I think is the access that is not available.
Okay.
Yeah. And the reason is of that is because the access has to do with using index, okay, to access the value at that particular position. But access using there's hash tables do not have any means by which they can be accessed using index. You notice it says not available. Okay. You can see the chart, right?
Yep. Oh yeah.
Yeah. You notice for access, under access in time complexity, under time complexity, for hash table, for Cartesian tree, and for split tree, they are not available.
Yeah.
Okay, because they don't make use of indexes as arrays do.
Okay.
Okay.
Gotcha.
So, but you can, for the other, what's it called? For the other data structures that have all this, you can implement all these four operations on them.
Gotcha.
Okay. Any other question?
Nope, that's it so far.
Okay. Can we look at hash map,
Yep.
hash table? Okay. When you actually basically look at the JavaScript, you know that there are different data types. You have the primitive data types, and you now have the category of data types that are referred to as objects, like
Yes.
functions, classes, objects itself, objects in JavaScript, and arrays. They are all classified as objects.
Yep.
When it comes to data type, okay? Unlike a language like Java, yeah, you have something like, I think it's hash map, right?
Right.
Good. But JavaScript does not have a data structure that is labeled or known as hash, either hash table or hash map. So the question will now be, what will happen when it comes to that? The simplest issue is JavaScript actually has a data type that is referred to as hash table.
Okay.
Yeah, the hash tables in JavaScript are known as objects because hash tables or hash maps, okay, there's maps, right, in JavaScript, right? And there's objects. So both of them, both maps and objects, data types, they actually have key value pairs.
Okay.
Right? So hash tables or hash map or dictionaries in Python has to do with any data type or any data structure or any data type in a language that stores key value pairs of any variable. So that is that for JavaScript. So both objects and maps, that's what they are, irrespective of the fact that different languages has its own, like in Python, you call it dictionary. And in Java, you have your hash maps and the rest of them. Another interesting thing, it's the way in which the language stores, what is it called? Stores, let's look at the way in which the language JavaScript stores objects. Unlike arrays, okay? You know, arrays, I told you that arrays are stored next to, the items of an array are stored next to each other.
Right.
But the same is not obtainable in hash tables. And that's why, because they are not indexed, that's why in that big old cheat sheet, the access is not available.
Gotcha.
Then the question now is, since hash tables are in contiguous memory or the items are not stored next to each other, how are they stored in, how are objects stored? Now, hash tables use something that is called hash function. I hope you can see this diagram, right?
Yep, I can see it.
Okay, good. Now, these are keys, like these are names of individuals and these are their phone numbers, right?
Right.
Not saying like, okay, you want to store an object of that has the keys as the names of individual and their phone numbers as the value. Just like, for example, let's use our phone book. That's the way we store the name of the individual and the phone number.
Right.
Now, for the language to be able to store these key value pairs, they get hashed, and the hash function will now choose where it will be stored. It's not going to be in sequential order. Like, for example, you notice John Smith, after the hash function has hashed it, okay, it is stored at position number 2 on the memory. Lisa Smith, it's stored at position 1. Sandra D is stored at position 14 after the hash function has actually hashed it.
Okay.
Now, the question will now be, how does hash functions operate?
Yes.
Okay. Okay, let's actually, are you a web developer?
Yes.
Good. Do you use Node?
I have before.
Okay. So that simply means that you understand how to hash a password, right?
For the most part.
Okay, have you used decrypt before?
It's been a while. But yes, I have.
Okay, you notice when you want to store a password, for example, the user or the client at the client side will actually provide, when he or she is filling something like a form, maybe like a login or sign in. Okay, okay, sign in. Let's start with sign in. Normally name, username, email, blah, 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 and password, right?
Right.
Now, when the user inputs the password and submits, on the other end, at the back end, because the developer knows that if the database gets hacked,
Hacked, yeah.
okay, that the hacker will be able to steal the passwords of the users, and who knows whatever his or her intention may be. So the safest way to store password is not to store it as plain text, but rather to generate a kind of to encode it so that it will be able to produce a kind of string value,
yeah,
that looks as something gibberish, okay, that does not make sense when you try to read it.
Yeah.
In English language, it doesn't make sense actually, and it's usually a one-way process. You can't reverse it back to the original. Rather, what you can now do, if the user wants to sign in, if the user provides the password, it compares it with the hashed password to see if they are the same. All right. Yeah. All right. So
yeah, that I've done before with like MD5, I think it's called.
Good. MD5, SHA-256, and all that, and all, those are hash functions. Okay.
Right.
Okay. There's a visualization page I'm on now. You have open hashing. Okay, but this one is not like sort of that kind of hashing of passwords in databases. All right. Now, these are our memories. Okay, can you see labeled from 0 to 12?
Yep, you froze for a little bit second, but I can hear you now.
Okay. I say below at the down part of this site, you now see a memory allocation labeled from 0 to 12, right?
Right.
Good. And at the upper part of it, you have a box where you can insert, where you can type in a value and you click on insert. It gets hashed, okay?
Yeah.
It gets hashed by this site. The hash function is not seen. Then it now maps out a particular portion where these are the memory spaces. It now maps that particular value to any of these memory space. You notice when I type, let's say 13, and ask it to insert, it hashes, okay? It has stored 13 at position or the memory space of 0.
Right.
Okay. Let's say I want to insert 30.
Okay.
It hashed it and it now stored it at 14. But this is not how array is stored.
Right.
Right? Array was stored at index number 0. Then the next item gets stored at index 1, just in that fashion. So this is what hash functions, this is what they do. This is what their operations are like. All right. Let's insert 14. All right.
Okay.
Let's insert 36. Okay. So you are seeing the way it hashes it and it chooses where it's going to store it.
Right.
This is just how hash tables actually work. The data structure, hash table. Okay. Now, you may be wondering, I told you that hash table usually has key value pairs, but I'm only typing in a number that's a value, right?
Right.
Good. What really happens is this number I cite, the hash function takes it, adds a key, hashes it, and chooses where to store it. And this one is storing now. It's the value. Remember the first stop I showed you, that diagram about storing it in a phone book, a name of a person and the phone number. Remember how it gets stored?
Right.
Okay, let me bring it up again.
Okay.
How it gets stored is this hash function. You notice is only the key that would be hashed, right?
Right.
After it has been hashed, the value will now be stored at a particular point. All right. And one thing you have to note is hash functions are very, very fast. Okay. That's one. So hash functions too will actually like if you give it another key, John Smith, okay, it will store the value at this particular position because it uses this name. After it has hashed it, it will now allocate it to memory space number 2. So every John Smith will go into this memory too.
Okay.
Okay. So, and another thing, that simply means that for every word, every corresponding word has a specific location, or every particular key has a specific location where it must be stored. It cannot be stored elsewhere. Okay. So by implication, you notice, inserting occurs at O of 1 because it's only one operation that will be done.
Right.
Okay, let me quickly go back to our big O cheat sheet. Yeah. Why is it taking time to load? Okay. Now, if you look at hash table, remember what I told you about access, why it's not available, because hash tables are not indexed. Then to insert an item happens at one operation. To delete happens at one operation. To search happens at one operation. But when you now look at the worst case, on average, right? Time complexity. When you now look at the worst, it now shifts from O of 1 to O of n.
Right.
Confusion, right?
Yep.
Yeah. Remember, I told you something. In big O, you consider the worst case, right?
Right.
Good. So you will always bear in mind the worst case that could arise from a situation. Then the question will now be, why is it so?
Right.
All right. Now, it is so because hash tables, just like any other thing as man has built, has never been perfect.
Right.
Yeah, that's the truth. None of us is perfect. In as much as we grow, we get better tomorrow or today than we were yesterday. But excuse me. Sorry, give me 1 minute. Let me clear my throat.
Okay, no worries.
All right, thank you. Hello?
No problem. Yeah, I'm here.
Okay. Now, you notice that something will happen. Like I was saying, that hash table, irrespective of the fact, average case in its time complexity occurs at constant time. Okay, let me show you first of all. Now, if you say delete, let's say delete.
Okay.
30. Did you see what just happened?
Yep.
Good. Let's say delete 14. It goes straight to it.
Yep.
It does not loop through from memory space 0 to the particular point because it does not have index. So both insert and delete operations, they happen at O of 1 or constant time. Okay, that's the average case. Now let's say we want to find, we only left with two values in these blocks of memory, right? Let's say that we want to find 36. It goes straight to 36, it finds it. Okay, let me put back, insert those other ones I removed. 30. Okay. Now, so let me insert one other one, 32. So you notice that the operations of hash table, because of this operation, because it's not indexed, it can easily insert, find, or delete anything. So that makes hash functions to be very, very fast in its operation. But the question now is, in its worst case, why is it O of n?
Right.
Before we understand that, we first of all have to look at the imperfection, let me use that word, of hash table. Notice something. I'm going to insert. Watch very well what will happen.
Oh, interesting.
Did you notice that?
Yeah.
Okay. Watch again. Did you see that?
Yep.
Okay. Now, it simply means if we keep adding, all right? If we keep adding, once the whatever the items that we are adding is hashed, it will be mapped at the same memory location, like for these ones. Okay, so they will map, the hash function maps the same memory location for different values, or for different keys, not values now.
Okay.
For different keys. And as that happens, you notice that there is a whole lot of values that are now stored in the same memory space. This is called collusion. Okay? This is actually called collusion. You now notice, if I want to access 14, if I want to access 14, I'll first of all have to come down to this memory space, check whether this first item is 14. Nope. I move over to this and check if it's 14. Nope. I move over until I get to 14. Okay. So do you now realize why the worst case is O of n?
Yep.
That is when collusion has happened. Let's find 14 so that you understand. Just watch what will happen. You get it right?
Yep.
So now searching for 14 will now occur at the rate of the number of items in the same memory space before 14. That is going to do 1, 2, 3, 4.
Right.
That's at O of n. If I want to delete 14, the same thing, the same process will be followed.
Right.
Okay. So that is why the big O in its worst case is at O of n.
Gotcha.
Okay. Now, this collusion that has happened, all right, let me insert 14 again.
Okay.
Did you notice something? That memory space 1 is linked to 14, and 14 is linked to 40, and 40 is linked to 1, and 1 is linked to 27.
Right.
Okay. Now, this has entirely produced another data structure.
Yes.
Called linked list.
Yeah.
Okay. Because in linked list, one just in that sequence until the last memory points to null or nothing. Like 27 is pointing to nothing.
Gotcha.
All right. Yeah. So that's exactly what happens. So this is the hash table. Then when you look at its space complexity, it should have been, its best case or average case should be O of 1. But because in big O, you consider the worst case, so it's at O of n. And this O of n occurs whenever there is what? Collusion. All right?
Right.
Good. So that is it.
Okay. Quick question for you. So with space complexity, do we just memorize? Because I understand how the speed complexity is working, but how do we calculate for the space complexity? Or do we?
Okay, let's go back to this hash, open hash
Right.
visualization. Okay, you notice in this place, all right, there's this memory spaces. There's no value occupying these memory spaces.
Right.
Okay, in position 10 or memory space number 10, it's only one value that is occupying it. Okay. Now in position 0, you have two values occupying the position 0.
Right.
Okay. And in position 1, you have 4 values. Now compare this 3. Okay, let's take 0, 1, 2. Okay, compare the 3 of them. Which one is using more memory space than the other?
1.
Okay, that's exactly how you calculate the space complexity. Space complexity simply means how much memory is this operation using.
Okay.
Good. So like, for example, when we want to find 27, you notice it's the first of all. Is that correct? Hello?
Oh, I just lost you for about, I lost you for about 20 seconds there.
Okay, let me go back.
Okay.
Okay, I said when you want to find 27, okay, it first of all comes to this memory space. All right?
Right.
And it will notice that there are 4 different values occupying this. It will now first check, is this 27? No. It moves over. Is this 27? No. It moves over. Is this 27? No. It moves over. Is this 27? Yes. Now,
right.
How many memory spaces has this search operation taken?
1, 2, 3, 4.
It has searched 4 different memory. Sorry, let me use the word 4 different memory spaces in the same location, right?
Right.
Good. And you rightly agreed that memory number 1 is using more memory than that of 0 and 2.
Right.
2 is using only 1, and 0 is using only 2, and
right.
1 is using 4. Let me use the word. They call like this memory space here is called a bucket.
Okay.
Okay, so 1 is using 4 different buckets. So that's how you now say that in its space complexity, all right, in its worst case, is going to take the number of items in that particular bucket. Like
right.
You have 4 in what we just saw.
Right.
So that's how you calculate it.
Okay. So it can increase or decrease by n, basically.
Yes.
Okay. Understood.
Okay. Any other question?
No, that's it for now. That makes sense.
Okay. So when you actually look at this, like I tried to say the other day, if you're now building, if one is actually building an application that you're going to search through, they are going to search through some data. You know what's case of an array, okay? Search it's O
of n.
n. In fact, it's only for all these other ones below, the B tree, red black tree, split tree, AVL tree, is actually has an improved efficiency, unlike this other one. So you now notice that you can now use, okay, implement, okay, to search. I can now implement red black tree so that my application will be more efficient, because if the person uses an array, as in if the person stores the data in an array, it won't be efficient. So this is data structures in an application. You can be able to combine the knowledge and build an application that is efficient.
Gotcha.
Okay. So that's the essence of knowing all this, as in knowing the data structures and their big O complexity, and the big O, both the time complexity and the space complexity, so that at any particular or given point, you can be able to employ the efficient data structure for that particular operation.
Gotcha.
Yeah.
Sounds good. So in these applications, like would someone, for instance, use an array, but and then when they did have a part of the application that does searches, convert the array to like a tree to search?
Sorry, can you come again? I didn't hear you clearly.
Yeah, sure. I was just wondering, so basically, like, do you use multiple data structures? So if you're building an application and let's say that for access, you use an array, but then for search, you'll convert it to a tree to do a search?
Yeah, this basically what it means to build an app that is scalable. For example, you told me that you've actually done web development. You notice one of the rules of writing codes, they will tell you keep it simple, don't repeat yourself, all that and all that.
Right.
All right?
Yeah.
Good. Let's move backwards a little. In ES5, when you want to implement a class, you use a function, right?
Right.
In EX6, when you want to implement a class that's an object, right? When you want to do OOP,
right,
you now use class, which is the ES6 standard to implement that. Now, by implication, you can actually do something with a function, and you can also implement class structure with a function, right?
Right.
But because you don't want to repeat yourself by implementing both operations with a function, you will now choose to do one with a function, and you now choose to do, the other operation with a class. Right. Is that correct? But in the same application. That's exactly what these data structures represent. They are meant to mimic those built-in data types. Let me use that word.
Okay.
All right. But now you now structure the operations so that they will not be, you don't use those inbuilt methods, okay, to implement them. Rather, you tend to restrict the user on certain things you want them to do just the way you want them to do it. That's the reason why, like I gave you an example before, that the operations of Twitter are quite different from the operations of Facebook.
Right.
Good. But when you check at the tail end of the day, it's still the same data structures that are being used,
right,
to build both applications. But you now notice that the way I'm going to operate Facebook is not going to be exactly the same way I'm going to operate Twitter,
Right.
because the owners of these applications have made it in such a way that they implement operations they want me to
Gotcha.
execute the way they want me to execute it. So these data structures are necessary because, like I showed you something the other day, when you want to search through a sorted array, that if you look through the array, you will now find, okay, for example, if you are going to look through 1 million data stored in an array, you will do from index 0 to the last index, which is like 1 million different operations, right?
Right.
Now, think about how slow it's going to be for the user, and think about how long it's going to take.
Right.
Okay. But you notice something like Google. Google has so much information, but within a split second, whatsoever thing that you want to search or you're searching for, you get the results.
Right.
Is that correct? So
yeah.
What made it so? What made it so is simply the data structures they chose and they implemented in building Google and using it to store the pieces of information that Google has. Now, back to what I showed you the other day, or back to what I was saying concerning looping through 1 million data stored in an array. You will notice if you use binary search to search through that particular or that same number of items stored in the array, you are going to do less than 20 operations.
Right.
When you use, we'll still get there, when you implement, because binary search trees, remember I told you it operates on what is called divide and conquer, right?
Right.
Good. It divides the total number of the structure, data, as long as they're sorted. It divides it into two. It keeps dividing and keeps searching through until it locates that particular value that you're looking for.
Right.
So you find out that, can you now compare if you are building, okay, let me just say, if you are building an app that you have to search through 1 million words, and you have competitors, okay, who do the same thing. Like, for example, when it comes to search engines, it's not only Google. There is Google, there are still some other search engines, right?
Yeah.
Good. So because of the competition, you want to be generating more traffic. So the available option for you is to use the right data structure that will give you efficient performance in your application. And once people notice that your application performs excellently well, they will come. They will come to use the application. But once it's not working as it should, they will first of all try to look for applications that are faster than yours. So that's just exactly the way it works. So in such a case, instead of looping through 1 million data in an array, you can easily implement that search operation by using a binary search tree, and it works out for you.
Right. Gotcha.
Yeah.
Okay. That makes sense.
Though remember, even as you're looking at it, there are trade-offs. Okay?
You said there are 3, what was that?
Trade-offs.
Oh, trade-offs. Yes. Gotcha.
Like I just showed you something concerning Hashtable. When you look at the average case, search, insertion, deletion, O of 1, but when you look at the worst case is at O of n, once there is collusion. But as long as there's no collusion, you get the average case.
Gotcha.
Okay. So there will always be trade-off between space and time.
Gotcha.
You use more memory to execute a particular operation, it occurs at less time.
Got it.
You use more time. You do an operation with less memory. It happens at longer time.
Right.
Okay.
Okay. Makes sense. Well, okay, I guess we can wrap her on up. Let's see. Oh yeah, because I got like 4 minutes and then I gotta go get the kids. But yeah, that sounds good. So should we meet same time tomorrow?
Yes.
Okay.
Yes. So by tomorrow we can look at what we need to attend to. We have a work on our hand.
Okay.
All right.
Yes.
Yeah, that correction or sorting that stuff out that
Right.
we ran into today. And if we have time, we should be able to look at, okay, maybe code implementation of Hashtable.
Okay.
All right.
Sounds
Yeah.
good.
Okay.
All right. And then your name is it Kelechi? Kelechi?
Kelechi, it simply means thank God in my
Thank
native
God.
language.
Kelechi.
Yep.
Got it.
Yes.
Oh, I love that.
Yeah. So, but the short form of it is Casey.
Okay, gotcha.
Yeah.
Okay. Well, sounds
Yeah.
good. All right. Well, I'll talk to you tomorrow then.
No problem.
All righty.
All right.